All right, properties of exponents. And I hope this is a review of college algebra. I hope you learned this in college algebra. Every time I taught college algebra, I always taught properties of exponents, properties of logarithms. But by definition, we say that if you have a positive integer for your exponent, that means repeated multiplication. So 3 to the 4th power is 3 times 3 times 3 times 3. I multiply by 3 4 times. The 1 power means I multiply by 3 one time, and so I get 3. The 0 power means I multiply by 3 0 times, so I get a 1. The exponent product rule goes like this. It says, what if I have x squared times x to the third? That would be like x times x times x times x times x. But multiplication has a property called, it's not the commutative property, it's the associative property. Multiplication is associative, and so since I'm just multiplying, I could get rid of the parentheses according to the associative property of multiplication, and this is just x to the 5th power. But if you think about, I don't just have to use 2 or 3, I could have used any numbers, and then I would get that many copies of x, and then in total, I just add together the number of copies of x that I'm multiplying, and that means this, that if I'm multiplying two exponents with the same base, I can just combine those into one exponent with the same base, and I add the exponents, okay? So then we get these identities for negative exponents. In other words, if you've got a negative exponent, you just take the reciprocal. And these are, in a way, a definition, like we're just defining that's how we're going to treat negative exponents. But this is the only way we could have defined negative exponents so that the exponent product rule is still true. In other words, when you are the first mathematician that decides to calculate with negative exponents, it's your job to define that. Like, what is that going to mean? We know that positive exponents, positive integers, means repeated multiplication. What does it mean to raise something to a negative integer power? How do we decide what that's going to mean? Well, they said whatever it means, it has to obey this rule. And if I were to have, let's say, x to the 3rd power times x to the negative 3 power, that should be equal to x to the power 3 plus negative 3. In other words, that should be equal to x to the 0 power, so that should be equal to 1. According to the product rule, this has to be true. So to stay consistent with the product rule, what's the only way to describe x to the negative 3 power? It would have to be like dividing by x to the 3 power. And it doesn't just have to be the number 3, but you can plug in the number 4, the number 5, the number 6. And the only way that this works, that x to the 3rd times x to the negative 3rd is equal to 1, and x to the 4th times x to the negative 4th is equal to 1, and x to the 5th times x to the negative 5th is equal to 1, is, well, if you're just taking the reciprocal. And so this is the only way that we could have defined negative exponents to make it satisfy the product rule. And then, of course, the same deal, the reciprocal of a reciprocal is, you know, that follows, I hope. The next is the exponent quotient rule. And the exponent quotient rule says, well, if I've got something raised to a power a minus b, well, that's like having a plus a negative b, and then the product rule that we discussed says that this is like x to the a times x to the negative b, And then the identities for negative exponents means this is how we interpret x to the power a minus b. So that's my exponent quotient rule. These are our identities for rational exponents. And again, in a way, these are definitions. This is how we are defining how we're going to treat a negative exponent. But in fact, it's the only way to define rational exponents. Oh, and shoot, I'm teaching this out of order. Man, I really thought I was careful about doing this, but I've got to do this first. Sorry. I'm gonna have to go back to this document and rearrange the order because I wanted this to be in a teachable order. I don't know why I kept the exponent power rule until property number 10, but it should be property number 6 or 7 or whatever. Okay, let's talk about the exponent power rule. Let's do this first and we'll come back to it. If I've got x to the 2 power raised to x to the 3 power, I've got x times x times x times x times x times x, right? Because x to the 2 power is x times x, and then when I raise that to the 3rd power, I'm taking that number and I'm multiplying it by itself 3 times. But again, multiplication is associative, and so I don't need the parentheses, and that's a total of 6 copies of x. But remember, it didn't matter that it was a 2, it didn't matter that it was a 3, there's nothing special about those numbers. What we're doing is we're taking that many copies of the x and creating this many copies of that many copies. And so really what it is it's a multiplication. It's 2 times 3 that gives me 6, and so the rule holds for all of the exponents. So that's how we get our exponent power rule. Now we can go back, and having explained that, this is the only way to define rational exponents so that the exponent power rule is true. Because what I need is that if I take the square root of a number and then I square it, I should get the number back, right? That's kind of the definition of how we set up square roots. Or if I take a number and then I square it, and then I take the square root, that should give me the number back. Right? This is kind of the definition of square roots, the definition of cube roots, the definition of fourth roots. Well, so then this is how we define rational exponents, right? Is if I have a number raised to some fraction, then this is going to be that root of that number. Or if I had like 64 to the 1/3 power, this is going to be the cube root of 64. And so the reason for this is because if I had, let's say, I don't know why I can't think of squares right now, 25 raised to the 1/2 power times 25 raised to the 2 power. Oh, sorry. This is what I'm thinking of. Because we're thinking about the exponent power rule, right? If I've got 25 raised to the 1/2 power, then raised to the 2 power, according to my exponent power rule, this should be 25 raised to the power 1/2 times 2, which is 25 raised to the 1 power, which is 25. In other words, however I'm going to define the 1/2 power, it has to cancel out when I compose it with the square. What's the only function that always cancels out when you compose it with the square? It's the square root. And likewise, if I had 8 to the 1/3 power raised to the 3 power, well, my exponent power rule says that this is the same thing as 8 raised to the 1/3 times 3 power. 1/3 times 3 is 1, and so it has to be 8. And again, what's the only function where if I compose that with the 3 power, I get back the argument? And the only function where that works is the cube root. The cube root of a number cubed gives you back the original number. So this is the only way that we can possibly define rational exponents. And if you're wondering about this last expression over here, keep in mind the product rule, right? Like if I've got a to the 1/3, or the power rule, I mean, raised to the 2 power, I should be able to multiply those and get a to the 2/3 power. But again, a to the 1/3 is the cube root. And besides, that's the same thing as a to the 2 power raised to the 1/3, isn't it? Because of the exponent power rule. So that's the same thing as the cube root of a squared. In other words, it doesn't matter what order you take the cube root and the square, whether you want to take the cube root first and then square it, or the square first and then cube root it, it's the same thing. So this is why we chose to define rational exponents this way, because it's the only way to keep that exponent power rule. This is a little bit esoteric, this is a little bit abstract, but property number 8 says, for irrational real numbers in the exponent, we define exponentiation as the limit of a sequence of rational numbers. So this is what I mean. Pi is an irrational number. You can't represent pi as a fraction. But what I could do is I could define a sequence of rational numbers. Because like 3.14, that's a rational number. I can represent that as the fraction 314 divided by 100. And I can create the sequence of rational numbers 3, 3.1, 3.14, 3.141, 3.1415, 3.14159. And if this is an infinite sequence, and you can see where I'm going with this, then it's going to converge to pi. So pi is the limit of this sequence. And the way I would calculate x raised to the pi power, where pi is an irrational number, is I could take the limit as n approaches infinity of x raised to these. In other words, I can get a better and better approximation of this exponent if I just take a number really far down in the sequence, right? Like an expression for pi that has 30 digits after the decimal. You can represent that as a fraction, so you can raise it to that numerator power and take the denominator root, and then you could get a good approximation of that. That's the idea. And that definition is useful too, because this implies that the exponent is a continuous function, because it always is equal to its limit at a given point along the real line, so it's continuous. For any positive real number base and any real number exponent, we know that the exponent's going to be greater than 0. In other words, you can't get a negative number, you can't get a 0 out of this. Because whether I do 3 to the 2 power and that's a positive number, or I go 3 to the 1 power and that's a positive number, or I go to 3 to the 0 power and that's a positive number, or even if I go 3 to a negative power, I still get positive numbers. I can't find a way to get a negative number using an exponential function. And then last, we've already discussed Euler's number at length. We've already proved that that's a limit that doesn't approach infinity. We've already proved that it's a limit that doesn't cycle or go chaotic or whatever. It's a good sequence that converges to a real number. Okay, when we plug the output of one function into the input of another function, we call that function composition. So like if I put the function g inside of f, I say that I have f composed with g. And if I plug in the entire function f into the argument of g, I say I have g composed with f. If I say the word identity function, I'm talking about a function whose output is the same as the input. In other words, the identity function is just the identity of whatever you're plugging in. This is the definition of inverse functions. We say two functions are inverse functions to each other if composing them in either order yields the identity function. So if I have f composed with the inverse of f, that will always give me the identity function. And if I have the inverse of f composed with f, that's always going to give me the identity function. Inverse functions come in pairs, which means the relationship works both ways. If f is the inverse of g, then g is the inverse of f. It's just like, you know, my brother's name is Jeff, so I could say Jeff is my brother, and Jeff could say Drew is my brother. It's a two-way street. The following functions are inverse to each other, right? Because if I were to take x cubed and then take the cube root, I've composed g composed with f, and I get back the identity function. And in the reverse order, if I take f composed with g, that looks like the cube root of x cubed, and I get back the identity function. These functions are also inverse to each other. And it would actually take a significant amount of work in handwriting to do this, right? To prove by composition that these are inverse functions. But I can do this on Desmos pretty quick. And the way that I could verify that these are inverse functions on Desmos is I could say f of x is equal to, and I already forgot what it was, x minus 2 over 3x plus 4. And then g of x is going to be equal to negative 4x minus 2 over 3x minus 1. And the way that I can check to see if these are inverse functions is if I take f of g of x, the green function is now the identity function. In other words, the green function is the function y equals x, because the input is exactly equal to the output. And that's how it should look if I compose any two inverse functions. Right? G of f of x also gives me the identity function. So that means f and g are inverses. More vocabulary, we say a function is strictly increasing if it goes up from left to right. And the maybe mathematical way of saying this is that x2 greater than x1 implies f of x2 is greater than f of x1. In other words, a part in your domain that's more to the right implies that that part of the range is going to be more up, right? If you think about the x-axis and the y-axis. So strictly decreasing means the opposite. It goes down from left to right. Monotone means it's either strictly increasing or strictly decreasing. That's the definition of monotone. We say a function is monotone if it is either strictly increasing or decreasing. Every monotone function has an inverse function. If a function is not monotone, then it doesn't have an inverse function. And for every positive real number base, the exponential function is monotone. In other words, this exponential function is going to be strictly increasing if a is greater than 1. It's strictly increasing. And if a is between 0 and 1, then the exponential function is strictly decreasing. And I guess maybe there's one little caveat to this that I should say, is like between increasing and decreasing, if you set a equal to 1, that's not monotone, right? Because it's constant. So I should say for every positive real number a not equal to 1, the exponential function is monotone. So that means the exponential function must have an inverse function, because every monotone function has an inverse function. What is the inverse function of an exponential function? A logarithm. Yeah, so prior to this point in college algebra, you don't know what to call that inverse function. And so we have to invent the logarithm to be this inverse. In other words, the logarithm base a is the inverse function of a to the x. And a to the x is the inverse function of the logarithm base a. So if I were to compose the two, exponent base a and logarithm base a, in either order, what I get back is the identity function. And this is the definition of the logarithm. This is how the logarithm function is defined. It doesn't have an identity on its own. It's only defined in the context of, like, listen, we've got these exponential functions. We know they're monotone. We know they have an inverse function. What is the inverse function? We don't know. It's not a polynomial. It's not a root. We're going to have to make up a function to be this inverse function. And we'll just call it the logarithm. And we'll use this notation for it. So it's a purely man-made invention, in order to give this exponential function an inverse. Okay, so when we say properties of logarithms, by definition, logarithms are the inverses of exponents, and that explains properties number 1 and 2. I compose two inverse functions, I get back the identity function. Property number 3 says, what if I want to convert an exponential function to an exponential with base e? And sometimes we call this the natural exponent because it has Euler's number as a base. And the way you should think about this is, remember that a is equal to e to the power natural log of a. And what I should have also defined already is this, that the natural logarithm is the logarithm base e. In other words, the natural logarithm is defined as the inverse of the exponent base e. So if I take natural log of e to the x, that gives me x. And if I really wanted to, I could rewrite it like this. I could call it the logarithm base e of x. That's what we call the natural logarithm. Any questions so far? I know I've been talking a little bit fast, but like I said, I'm hoping that some of this is just a review of the college algebra essentials. So if I say a is equal to e to the power natural log of a, that's because I'm composing two inverse functions. And so the e and the natural log can cancel each other out, and I just get a. Then the next thing is, if I wanted to have a raised to the x power, that would be like e raised to the power natural log of a raised to the power x. And now remember the property of exponents that says if I've got e raised to some power, then parentheses raised to another power, I can just multiply those two powers, and this is what I get. That's my exponent power rule, right? And so I can always convert any exponential function into an exponential function with base e using that formula. That's going to come in handy later when we do derivatives. The logarithm of 1, right? We say that the logarithm of any base of 1 is equal to 0. And we say this because if I were to take a raised to the power logarithm base a of 1, and on the right side, this would be equivalent to a equals 0, well then the exponent and the logarithm cancel each other out, and I get a 1, and any exponent raised to the power 0 is 1. And so I wrote this proof backwards. Really, the proof should start off with saying, everybody, let's agree that 1 is equal to 1. And if I want to, 1 is the same thing as a raised to the power logarithm of a of 1. And if I want to, 1 is the same thing as a to the 0. And since these are raised to the same, or sorry, they have the same base, these exponents have the same base, then to be truly equal to each other, the exponents have to be equal as well. And so that's how we end up with this identity. Okay, what if I have a logarithm base a of a? Well, a is the same thing as a to the 1 power, isn't it? And so if I cancel out the 2, then I just get 1. I don't know how else to say it. But since the logarithm is the inverse of the exponent, these cancel out when I compose them, and I just am left with that 1. Okay, property number 6. For any non-positive real number, we say that the logarithm is undefined. So a logarithm of 0 is undefined, and a logarithm of any negative number is undefined. So the logarithm is, of course, the inverse of the exponential function. So we choose a value of a. And every inverse function has this special kind of symmetry. It's bilateral symmetry across the identity function, across the line y equals x. So this red logarithm curve is going to be the mirror image of the blue exponential function curve. And since the exponential function curve is getting closer and closer and closer to the x-axis as I go off to the left, when I flip that across the green line and I make the mirror image, this red curve is now going to get closer and closer and closer to the y-axis as I go down. But just like the blue curve doesn't exist below the x-axis, flip that, mirror that over the green line, the red curve doesn't exist to the left of the y-axis. So the red curve, the logarithm function, is not defined for any negative numbers. The logarithm product rule. So what if I have this? Hopefully we can all agree that x times y is equal to x times y, right? I'm going to set my notes and make sure I don't make it a little, yeah, okay. That's what I thought. If we can all agree that xy is equal to xy, then on the left side, let's take the logarithm base a of x times y. And on the right side, actually, let's do two things. There we go. That's what I want. So notice this is the same. This is the same. And this is the same. On the left side, I'm treating the product together, but on the right side, I'm treating those variables separately. But again, I'm just composing inverse functions. They cancel out. They're equal to each other. Now, the trick is a property of exponents. The property of exponent says if I'm multiplying these two exponents that have the same base, I could combine them into one exponent. And what do I do with these little powers here? What do I do?
Add them.
Yeah, I can add them. And so on exercise 2 of your homework, when it says, be ready to understand and prove any logarithm property, what I'm talking about is this, is write something like I've shown you in this blue pen. And the argument says, well, we know the exponent rules work. We've already discussed and explained those exponent rules. And if we're willing to accept that this exponent product rule works, and this left side is really equal to the right side, and they have the same base, the only way that's possible is if the powers are also exactly equal to each other. And that's how I can rest assured that this logarithm product rule always works. Does that make sense every step of the way? And then here's the logarithm quotient rule. And for the quotient rule, it's really similar. You do a few of these and you start to get the cadence for like what you do. We're going to agree that x divided by y is equal to x divided by y. On the left side, I'm going to take a raised to the power of logarithm base a of x over y. On the right side, I'm going to take a raised to the power logarithm base a of x divided by a raised to the power logarithm base a of y. But we have an exponent quotient rule as well. And the exponent quotient rule says if I'm dividing two exponents that have the same base, I could just keep the same base. And what do I do with the powers? Subtract. So then we subtract these powers. And since the left side of the equation should be equal to the right side of the equation, and they have the same base, the only way that the left side is always equal to the right side is if the powers are exactly equal to one another. So then we write down our desired logarithm quotient rule. Does that line of reasoning make sense? Okay. The logarithm power rule, I bet you can already guess what we're going to do. But we're going to start off by saying x to the power y must be equal to x to the power y. And then we'll take a raised to the power logarithm base a of x to the power y. And on the right side, a raised to the power logarithm base a of x raised to the power y. And now on the right side of the equation, what exponent rule are we going to use to complete the proof? It's that exponent power rule, right? Where if I'm raising this to a subsequent power, I could just multiply the powers. And then now, since the left side is supposed to be equal to the right side, and they have the same base, the only way I can make these always equal to each other is if they also have exactly the same powers of a. And so that's how we end up with our logarithm power rule. That's how you would prove it. And it's 4-step proof. Property number 10 says the change of bases formula. I always have a hard time remembering this proof, but I do remember how the end goes. And maybe I'll show you how I would reconstruct this on test, because I also like, sometimes to try to teach you test-taking skills. If I can't remember how the proof starts, at least I can remember how it ends, right? I know that the last line of my proof has to look like this if I'm going to prove that. And then let's see if we can work backwards to get the right answer. And by work backwards, I mean I'm going to write the line log base b of a times log base a of x is equal to log base b of x. Do you see what I did? I said I don't like that denominator. I'm going to multiply both sides by that. And then what I'm thinking is, what did I just learn in property number 9? If I'm multiplying something times a logarithm, I could make that something into a power on the inside of the logarithm, right? That's my logarithm power rule. So let's do that. I can write logarithm base a of x to the power logarithm base b of a. I really thought that was the way this is going, but I'm not 100% seeing the next step here. Let me refer to my notes and see if I got it written down. Oh yeah, well. Oh, okay, I see. I did the wrong thing. What I really should do is make this log base b and make this one the log base a. Okay, so let's talk about that. It's the same trick. I remembered the right trick, I just did it with the wrong logarithm. So instead of taking the log base b and putting it on the x exponent, what we're going to do is we're going to take this thing, log base a of x, and put that on the exponent of the a, using the same logarithm power rule. Okay? So reconstructing this, I've got a to the power log base a of x inside the log base b. Now, I bet you can see where this is going finally. If we could just agree that logarithm base b of x is equal to logarithm base b of x, then the first step is doing this inverse function composition, because this is the same thing as x. And then the next step in the proof is using the logarithm power rule to take this log base a of x outside of the logarithm base b of a. And then the last step would just be to divide by logarithm base b of a. So, like I said, that one's always difficult for me to remember, but I just write what I'm trying to find first, and then I try to recreate it going backwards. And if you run into a snag and you can't remember the full proof, write down what you can, put a star next to it, finish the rest of the test, come back to it, you got some time at the end of the test, keep thinking about it. To refresh, we start off by saying the logarithm base b of x is equal to the logarithm base b of x. Nobody can argue with this. What happens in this step, Carter? From here to here.
Your bases cancel.
Yeah. Those are inverse functions, the exponent base a and the logarithm base a, so they cancel each other out, and it's the same as in the previous step. I'm just writing it differently. Okay, Anna, what's happening from line 2 to line 3 here?
You separate them.
Yeah. This is what I've called the logarithm power rule on your properties of logarithm page I handed out yesterday is that if I've got a power happening inside the logarithm, I can just take it out and multiply by that power instead of having it on the inside. And then last step, what goes on from here to here, Avery?
You're dividing by log b.
Yeah, divide both sides by log b of a, and that gets us our change of basis formula. So property 11 says the natural logarithm is the inverse of the exponential function e of the x. We compose two inverse functions. The result is the identity function. I'm going to leave myself a note for next time because I remembered just now that next year when I teach this class, I need to change the order of the properties of logarithms so that number 7 is the power rule. Okay. Property number 12 says, now if I want to convert to the natural logarithm, that means I have like a logarithm with any base and I want to convert that to a natural logarithm. This is the formula I would use. And this is a really simple proof because property number 10, which we've already proved, says the logarithm base a of x is equal to the logarithm base b of x divided by the logarithm base b of a. Now set b equal to what?
Which side is the natural log?
Yeah, the natural logarithm is actually the logarithm with base e. So if I take that change of basis formula and I set the b equal to Euler's number, then I get the logarithm base a of x is equal to the logarithm base e of x over the logarithm base e of a, and that is the natural log. This is a formula that's important for calculating things because when I teach college algebra and we use the TI-30X2S calculator, the TI-30X2S can do natural logs, but it can't do a logarithm of any base, right? If I ask you what's the logarithm base 2 of the number 5, your TI-30X2S calculator can't do log base 2 of 5, but it can do natural log of 5, and it can do natural log of 2. So if you take natural log of 5 divided by natural log of 2, you get the logarithm base 2 of 5. And this is something we discussed yesterday, in fact, in my numerical analysis class. Because in numerical analysis, we talk a lot about how computers actually perform calculations. Because at the core of it, a computer can only do 4 things. A computer can only add, subtract, multiply, and divide numbers. So when you tell a computer something like, take the logarithm base 2 of 5, how does your computer do that? You have to give it a sequence of instructions that only involve add, subtract, multiply, and divide. And that's what the whole numerical analysis course is about. And the first step in this process is you tell your computer, all right, logarithm base 2 of 5 is equal to logarithm natural log of 5 divided by natural log of 2. And then we define the natural logarithm as a particular integral. If you're really curious, I'll tell you what that is really fast. Because what's the derivative of the natural logarithm? 1 over x, right? So that means natural logarithm is the antiderivative of 1 over x. So if I take the integral from 0 to x of 1 over t dt, that's going to give me my natural log of x function. And what we do in numerical analysis is then we say, all right, anytime I want the log base 2 of 5, I'm going to take that to be the natural log of 5 divided by the natural log of 2. And then how will I calculate the natural logarithm? Well, I'm going to take this definite integral. Of course, my computer can't take this definite integral the way we've been doing in class. Like, it can't take the antiderivative and plug in x, plug in 0, because taking the antiderivative means the natural logarithm. And we're trying to talk about how do you solve the natural logarithm with just add, subtract, multiply, and divide. And the answer in our numerical analysis class takes about 3 weeks to talk about, right? How to solve this integral with only add, subtract, multiply, divide. It's a really interesting topic. Very cool math that goes down that rabbit hole. But it is important to be able to convert to the natural logarithm. Okay, the next thing is the logarithm reciprocal rule. So what we start off by saying is, well, 1 is equal to 1. Everybody can agree. That means the logarithm base a of a to the 1 power is 1, since the logarithm base a and the exponent base a are inverse functions. And then, if the logarithm base a of a is equal to 1, and I guess we've already proved that before, so we could have just started from this line. This was one of our earlier properties of exponents that we've already proved. So then we say, it must be true that the logarithm base a of b raised to the power logarithm base b of a is equal to 1. Because b raised to the logarithm base b of a is equal to Leah, what is this equal to in orange? What is b to the power log base b of a? Antonio? What is this equal to? What is b raised to the power log base b of a? Olivia, what is b raised to the power logarithm base b of a? It's not 1. Ian, what is b raised to the power logarithm base b of a? Hey, thank you. Right, because this is the definition of the logarithm, that the logarithm is the inverse function of the exponent. And if I compose two inverse functions together, they just cancel each other out. So b to the power log base b of a is a. And that's what's happening here. That's the logical step in the proof. Okay. The next thing we're going to need to do is use the logarithm power rule. It's one of the earlier properties of logarithms that we've already proved. And the logarithm power rule says, if I've got a power, log base b of a, inside my logarithm, I can take that out of my logarithm and just multiply. And having taken it out of the logarithm, that's what it looks like. What's the last step here that I have to do, Hudson?
Put size that one base b of a?
Yes. If I just now divide both sides by a logarithm base b of a, I get 1 divided by a log base b of a. That's it. That's what I've been trying to prove.
So on our test, like, will we have like a page that's just like we have to prove like all of the properties of logs, like we have like derivatives?
So, it's not going to be all of them, right? You only have 75 minutes for your test, and so I can't give you every single one. Likewise, I can't give you every single, derivative power rule that we were talking about a few days ago, whenever I gave you the definition of the derivative and I said, prove that the derivative of x squared is equal to 2x using the definition of the derivative. I can't give you all of those, but I'm going to give you some from every lesson, right? 1 or 2 proofs from every lesson to reproduce on the test. And for this last test, I'll also, I don't know, I'm still thinking about it. For this last test, I might give you a more narrowed down study guide too as we get closer. But regardless, the test is going to be based on homework questions. So if you practice the homework questions, you will be good to go on the test. I won't include anything on the test that's not on the homework. So the homework is a perfect study guide. All right, so finally we're moving on to derivatives. We're finally doing some calculus. And now I want to show that the derivative of the natural logarithm is 1 over x, using only the sort of mathematical tools we've built up so far. And so what I know about the logarithm is that the natural logarithm of x is the inverse of e to the x, which means that if I were to take the natural logarithm of e to the x, I get x. And if I get e to the power natural log of x, that cancels and that just gives me x. And that's the way we defined the natural logarithm. We really don't know a lot. Actually, we do know quite actually a bit about the natural log. In fact, we may not even use this. I'm having trouble remembering the entire proof right now, but I can get us started. And sometimes my memory gets jogged if I just start. So what's the definition of the derivative? If I want the f prime of x, what is that defined as? It's a limit, right?
Limit of 0 to infinity, or h to infinity?
It's the limit as h approaches
0.
0 of f of x plus h
F plus, or minus f of x,
minus f of x
and then h.
divided by h. Yeah, that's a good thing to have memorized. And so whenever I'm thinking about taking the derivative of the natural log, what I'm going to immediately do on the left side here is say, well, the derivative of the natural logarithm, according to my definition of the derivative, is that this would be the limit as h approaches 0 of natural logarithm of x plus h minus natural logarithm of x divided by h. Right? That is just the definition of what it means to take a derivative. Okay, so I have all of these properties of logarithms at my disposal here in order to make this simplify. Because if I were to try to directly evaluate this limit and plug in h equals 0, I get natural log of x plus 0 minus natural log of x. That's a 0 divided by 0. 0 divided by 0 is undefined. So what do I do instead? I'm going to refer to a property of logarithms that I got to find here, this one. Where I am currently in my proof, I've got a logarithm minus another logarithm, and they're both natural logarithms, so they have the same base. What I could do is I could combine it into one logarithm where I'm dividing on the inside of the logarithm instead of subtracting. So let's do that. Let's use my property number 8, logarithm quotient. And that's going to give me the natural logarithm of x plus h divided by x, all divided by h. So that's one of the reasons we discussed the entire way through the properties of logarithms. And, you know, I'll say this just for a second. Is like, when we got to this point and I said plug in h and you get 0 divided by 0, you know, like 0 divided by 0, that's an indeterminate form. We've used L'Hopital's rule in the past for indeterminate forms. There's two reasons I don't want to use L'Hopital's rule right now. Number one, I haven't proved L'Hopital's rule. And so if we're thinking about math history and how people invented calculus, they wouldn't have had L'Hopital's rule to do. But the second reason, and the more important reason, is if I were to try to use L'Hopital's rule asks me to take the derivative of the numerator and the derivative of the denominator separately. And that means taking the derivative of the numerator, which means taking the derivative of the natural logarithm function. Only the whole point of this proof is to find what is the derivative of the natural logarithm, right? And so I don't want to create circular logic by saying the derivative of the natural logarithm is the derivative of the natural logarithm because it's the derivative of the natural logarithm. That's not, it's not good logical hygiene. Okay, so I'm going to rearrange this just a little bit, and hopefully everyone agrees with where I'm going, but see if you buy this. So instead of dividing by h, I can multiply by the reciprocal. And then where I have x plus h over x, I can do x divided by x is 1, and then add the plus h over x. And at this point, I need to make a substitution. I have to think for just a moment about what that substitution is going to be. Because I know that I'm going to need 1 over h to instead look like n divided by x. And then if 1 over h is equal to n divided by x, what would h over x look like? Maybe I shouldn't ask that question right away. What would h be? It's the reciprocal of 1 over h, so that would be x over n. And then now if I want h over x, that would have to be 1 over n. Okay, so this is important because I'm going to replace that. This is important because I'm going to replace this. And these imply these imply these. So now let's make that substitution here in our limit. One over h is now n over x times the natural log of 1 plus 1 over n. And there's one other thing that we need to discuss, which is what happens as h approaches 0? If h is approaching 0, what happens to n? If h is approaching 0, then 1 divided by h is approaching infinity, right? So n would be approaching infinity. Make sure you understand why. X is just, imagine like x is like a constant. It's just something we're plugging in. When we take this limit, we're not worried about the x changing. The limit is only concerned with the h being the variable that changes. And so as h is approaching 0, and I'm trying to replace the h's with this n, I'm asking what would n have to do as h approaches 0? And if I've got 1 divided by a number that's shrinking down to 0, 1 divided by a number that's getting tinier and tinier and tinier as h approaches 0. This 1 divided by h is going to become bigger and bigger and bigger. It's going to grow toward infinity. And if x is just some number we're plugging in, n is going to have to take on the burden of growing to infinity. So n blows up to infinity when h approaches 0 because of that reciprocal relationship here. And that means we're now taking the limit as n approaches infinity, and my substitution is complete. I have managed to substitute every appearance of the variable h with the variable n in the substitution. So now, I'm going to use a property of logarithms again. We love our properties of logarithms. And this time, where I'm multiplying this entire logarithm by n, I can use that logarithm power rule. I'll scroll up so you can see it. I'm going to use this. Going from right to left, if I have something that's multiplying the logarithm, I can put that inside the logarithm and make that a power on the inside of the logarithm. That's what I'm going to use as property number 9. And so this is what it looks like to apply that property number 9. And where I'm multiplying by n, I'm now going to make n a power on the inside of my logarithm. There's a certain property of limits that we know is going to be such that, like, if I'm taking one limit times, like with a multiplication inside, if I'm taking the limit of a product, that's what I'm trying to say. I'm taking a limit of a product of 2 different factors, this factor times this factor. I can separate that limit into 2 different limits. I can take one limit of 1 over x as n approaches infinity times another limit as n approaches infinity of the natural log stuff. There are no n's in the first limit, right? 1 over x is just, as n approaches infinity, going to be 1 over x. What about the second limit? Well, because the natural log function is a continuous function, and you can only do this with continuous functions, but since the natural log is a continuous function, I can switch the order of the limit and the natural log. As long as you have a continuous function, then you can switch the order of the limit and the natural logarithm. All right. Now, a quiz for everybody. Kyle, what is the limit as n approaches infinity of 1 plus 1 over n to the power n?
One?
No.
No?
Gabe?
Is it infinity?
No. Carter?
I know I've seen it, I just don't remember.
Avery?
I don't think I know.
Is it like a algorithm?
Anybody? What's the limit as n approaches infinity of 1 plus 1 over n to the power n?
Oh, it's a huge number.
That is Euler's number. This is the definition of what it means to be Euler's number. Is to be that limit. So we've got 1 over x times the natural log of e. What is the natural log of e? 1, right? Because e is the same thing as e to the 1 power. And then the logarithm base e cancels with the exponent base e. And this is 1 over x. What were we trying to prove this entire time? We were trying to prove that the derivative of the natural log function is 1 over x. And we said we don't want to use L'Hopital's rule. We don't want to rely on the derivative of the natural logarithm to tell me what the derivative of the natural logarithm is. We're trying to put ourselves in like the shoes of like a, 1600s mathematician in Europe somewhere, working through inventing the calculus. It's like, what do you do? What do you do if you want to find out what the derivative of natural log is? Well, this is probably somewhat similar to what they would do, is they would rely on their definition of the natural logarithm, these properties of logarithms that they've been building up. Slowly work through it one step at a time. This substitution is really critical. Like if you wanted to reproduce this proof, you'd have to use a substitution. And you have to remember what that is, which is not super easy. I could see this maybe being a bonus points question. This wouldn't be like one of the core bread and butter 100 points on your test, but this might be like an extra bonus 10 points question. Because this is a long proof. I think your basic questions that are part of the integral 100 points, that's going to be like 5-line proofs. And this is more of like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10-line proof. So it's a little bit more tricky, a little bit more to remember here. And it's funny, on the one hand, I could never, ever memorize Shakespeare, right? Like if I had to be an actor and like get on stage and deliver memorized lines, like that sounds incredible to me, like that somebody can like memorize a sonnet and just deliver it word for word. what I'm actually doing when I remember these proofs in class is I'm just kind of pathfinding, you know? Like, it's a logical idea to start off with the definition of the derivative. And then I don't have to remember the next step because this just looks fishy to me, right? Like, I just see subtracting two logarithms, and the thing that I immediately want to do is condense them. And then when I have this, I think, well, okay, dividing is the same thing as multiplying by the reciprocal. And I have these sort of like next steps in my head that make it so much easier to remember. And maybe that's not the same for everybody, but like I think that memorizing proofs is easier than memorizing prose or poetry because there's actually like logical next steps you can try. And if you ever make a mistake in a proof, which I do all the time, that's why your pencil has an eraser. If you hit a dead end, erase it, go back to where you think you were making good progress and try something else. So I don't know. Maybe that's just me. The next thing we're going to prove is the derivative chain rule. And the derivative chain rule goes like this. It says if I want to take the derivative of a composition of functions, like f composed with g, this is first taking the outside derivative and then multiplying by the inside derivative. And the proof looks like this. We're going to use the definition of the derivative. So that the derivative with respect to x of f of g of x is going to be the limit as h approaches what, Gabe?
0.
0. Thanks. Of this time, it's going to be f of g of x plus h minus f of g of x divided by h. That's the definition of the derivative. But this time my function is f of g of x, not just f of x. I'm going to rewrite this again. But this time, I'm also going to multiply by 1. And what I mean by multiply by 1 is, more specifically, I'm going to multiply by g of x plus h minus g of x divided by g of x plus h minus g of x. I'm going to keep using the same colors. Let me color code this better. So I've got, again, man, the worst part about this proof is just how much you have to write. It's not even a hard proof. It's just like hand cramps. Okay, now I'm going to steal this part of the denominator and move it over here. Because it's the same. You know, multiplication is commutative. I can switch the order here. And then I get like this. And I can separate these limits. Like, I didn't leave enough room for me to write here, but I can separate this limit where I'm multiplying these two factors in my product. Oops. So that the second limit is just the definition of what it means to take the derivative of g with respect to x. And this first one requires just a little bit of, I don't know, a little bit of consideration here. Let's go back to my definition of the derivative for just a different function f and think about that for a minute. If I want the derivative of f, we say that's the limit as h approaches 0 of f of x plus h minus f of x divided by h. Oops. H is the same thing as x plus h minus x. And now if you look at this definition of the derivative, where I replace the h with x plus h minus x, and that's still h, but I just wrote it differently. Hopefully I can convince you that this is what it would look like to take the derivative of the outside function, but leaving the inside function alone. Because now instead of x plus h minus x, I have g of x plus h minus g of x. And so this would be the derivative of f with respect to g, but not taking the derivative of g. This is what it would look like to take f prime of g of x. And that's probably the biggest leap in this proof. The biggest thing you have to buy into and believe here is that, like, this is my definition of the derivative, yes, but h is the same thing as x plus h minus x. And then where I have g of x plus h minus g of x, all I've done here in both the numerator and the denominator is I've put a little middleman, g, as a way to convert from the x domain to the g range. And since that's getting plugged into the argument of my f function, this is what it looks like to take a derivative of f of a function g, but not take the derivative of g. And then, of course, that's what it looks like to take the derivative of g. So again, since I'm multiplying, I can separate the limits, and that's exactly what I've been trying to prove, is that derivative chain rule works. Okay, I think that's the last really difficult one. I think the rest of them should, I hope, be a lot faster and easier. Like this one. It says the derivative with respect to x of e to the x is e to the x. And again, what I know about e to the x is a few things. Well, I know that e to the power natural log x is x. And I know that natural log of e to the x is x. And I know that the derivative of natural log of x is 1 over x. And I also know that the derivative chain rule works. So we're allowed to use the chain rule now. What do I do with this? I would say, let me start off by trying to take the derivative of natural log of e to the x. But of course, natural log of e to the x is x. We already said that. So on the right side, the derivative of x with respect to x is 1. And on the right side, the derivative with respect to x of natural log of e to the x is going to require the derivative chain rule, where I first take the derivative of the outside function. The derivative of the outside function is the derivative of natural log, so it's going to be 1 divided by the argument. And then I multiply by the derivative of the inside function. And I don't know what the derivative of that inside function is. Right? You got to play dumb in order to prove something. We don't want circular logic. We don't want to say, it is what it is. So instead, we don't know what the derivative of e to the x is yet. But what I can do now is I'll just multiply both sides of this equation by e to the x. And after I multiply both sides of this equation by e to the x, 1 times e to the x is e to the x. The e to the x cancels. And that completes the proof. Yeah, I told you that one would be easier.
We should do a bunch of those on the test.
But we had to find the derivative of the logarithm before we could find the derivative of e to the x, because notice we needed the derivative logarithm. We also needed the derivative chain rule. All this stuff builds on each other, Like you've got to construct it one brick at a time. You can't build the roof before you build the walls. All right. Theorem, x to the a equals a. This is the power rule. This is my derivative power rule. And previously in class, we proved that the power rule would work for x to the 2 power, and x to the 3 power, and x to the half power, and x to the negative 1 power. We proved that the derivative power rule works for a bunch of different powers of x, but we didn't prove it in general. Like, how do I know the derivative power rule is going to work for x to the power pi, or x to the power 5/7? We're now trying to prove the derivative power rule works in general for any real number a. For any real number a. And so the proof goes like this. I say, I'm trying to think about the number x. And I remember that x is the same thing as e to the power natural log of x. So if I have x to the a power, that means I've got e to the power natural log of x raised to the a power. And there's a certain property of exponents I want to use now to say that this is the same thing as e raised to the power a times natural log of x. Okay, so I've got two subsequent exponents. I just multiply the exponents. Now we're trying to take the derivative of x to the a power. So we're trying to take the derivative of e to the power a times natural log of x. And to do this, we need the derivative chain rule. And the chain rule says first take the derivative of the outside function, and e to the stuff will have the derivative e to the stuff. And then I have to take the derivative of the inside function and multiply, so I get to multiply by, what's the derivative of a times natural log of x?
1 over x.
It's what?
1 over x.
It's not 1 over, natural log would have the derivative 1 over x, but what about a times natural log of x?
A over x.
A over x.
Oh, so you don't do, like the natural log of a wouldn't be 1. I mean, the derivative of a wouldn't be 1. It's not.
So if you just had a constant, the derivative of a constant is 0.
Oh.
But if you have a constant multiplying a function of x, then it's the derivative homogeneity rule, where you just take you keep the constant factors. Yeah. All right, well, we just said a moment ago that e raised to the power natural log of x, sorry, what did I say? E raised to the power a times natural log of x is equal to x to the a. And so I can apply that same logic here and say that this is x to the a power. But I'm going to multiply by a and divide by x. And so when I multiply by a, I can write a times x to the power. What happens to x to the a after I divide by x? The new power becomes a minus 1. Because if I divide by an x, now I'm multiplying by one fewer x, right? And so by that repeated multiplication definition of the exponent, we say that x to the power a divided by x is x to the a minus 1. And that completes the proof. That is the proof of the derivative power rule. But it's funny, the derivative power rule is like the easiest derivative to remember. Maybe not as easy as derivative of sine, but like it's pretty easy in terms of derivative rules to remember. But if you want to prove the derivative power rule works for any real number a, first you have to be able to take the derivative of e to the x, right? We had to prove that. And we also have to be able to take the derivative of natural log, and we also have to be able to know the chain rule. We also have to know derivative homogeneity. And so again, all this stuff is just building on each other. There's a very delicate order to the way you're allowed to prove things if you're trying to construct calculus from the bare ingredients. But are there any questions about this proof? Everybody get it? Okay. Looks like we've got 2 more left in this set of notes. This is the derivative of any exponent in general. It's not just e to the x, but it's for any real number a. And the trick is very similar to the last one. I'm going to say that a is e to the power natural log of a, so that a to the x is e to the power natural log of a raised to the power x, so that a to the power x is e to the power natural log of a times x. And now we want to take the derivative of a to the x. So it's like the derivative of e to the power natural log of a times x. We just have to be careful about the way we take the derivative. So I'm going to use the derivative chain rule. And the derivative chain rule says we start by writing the derivative of the outside function, and the derivative of the e to the stuff is going to be e to the stuff. And then the derivative chain rule says I'm going to multiply times the derivative of the inside function. What's the derivative of my inside function? What do I multiply by for this chain rule? I've already done the derivative of the outside function. Now I need to multiply by what?
Would be x over a.
Because I'm taking the derivative with respect to x. A is just a constant.
1 over a.
A is just a constant. So that means natural log of a is also just a constant.
So it's just 1.
This is just x.
X. So it's just natural log of a.
There you go. Kyle's got it. Great job, Kyle.
Wait, what?
Because this is a constant number times x, and I'm taking the derivative with respect to x, right? It's like 3 times x. What's the derivative? It's 3, you know? Yeah. I know it's confusing now because a is a letter and not a number, but we're pretending that a is a constant. A is just any real number you want to choose here. Okay, so then the next step is we say, all right, I've got this big ugly e to the natural log a times x. But e to the power natural log a times x is the same thing as a to the x. So I'm ready to write my answer. It's just a to the x times natural log of a. And that's the proof. Questions about that one?
I'm messing with the last 3 for sure. Those are definitely more doable in my brain than the
Mm-hmm.
other ones.
I'm glad. One more. One more. This is the last one for today. We are trying to take the derivative of a logarithm of x, and this time a is just any real number. A is not a variable, and it's not necessarily the letter e, but it's going to be any real number we want to choose. Actually, I take it back. That's a lie. Because I don't know if you're allowed to put in negative numbers or not. That's something I've never really thought about before. So let's assume a is a positive number. Just because I don't know what logarithm base 0 is, like logarithm base -1. That may or may not even be a possibility for a thing you can do. It's not a possibility. You know how I know? Because the logarithm base a of x has to be equal to the natural log of x divided by natural log of a. So if I have, yeah, exactly. If I had natural log of 0, that's undefined. If I have natural log of a negative number, that's undefined. So I can't do that. In fact, the base does have to be a positive number, or the logarithm's not defined. So we've got only positive number bases. Very good. So for any positive real number a, what is my derivative of the logarithm? Well, we are actually going to use that fact, I believe, to say that the logarithm base a of x is the natural log of x divided by the natural log of a, that change of bases formula that we proved earlier. So that now when I'm taking the derivative of the logarithm base a of x, it's going to be the derivative of natural log of x divided by natural log of a. And what is that derivative?
It's the quotient rule thing.
It's not.
Is it undefined?
So imagine it like this. Dividing by a natural log of a is the same thing as multiplying by the reciprocal, okay? But again, a is just a constant. A is not a variable. That means natural log of a is just a constant. It's not a variable. That means 1 divided by natural log of a is just a constant. It's not a variable. It's just a number. So what is it, Hudson?
So you can just leave the natural log of a on the bottom and take the derivative of natural log of x, which is 1 over x.
Perfect.
That's just the answer right there.
Yes. Yes. I'm leaving the 1 over natural log of a alone because of the derivative homogeneity rule. I just leave constant multipliers alone. I leave the constant factors there. They don't do anything in the derivative. But the derivative of natural log of x is 1 over x. And so that's the proof. The key to understanding this is to know this change of basis formula. That's why we proved it earlier. And so if I asked you to prove this on a test, I would want you to write the change of basis formula. And then, I guess just writing exactly what I wrote in blue, that would be sufficient for your proof on a test.